Hello, welcome to Electronics Education. This is Vincent Chang. In this lecture, I'm going to present a simulation of enhancement MOSFET. Simulation of enhancement MOSFET. Let's start with the N-channel enhancement MOSFET. The device structure is shown on the left-hand side. It's the N-channel. Source, 4-terminal device, gate, drain, and body. Source, gate, drain, and body. On the right-hand side is the circuit symbol. Source, gate, drain. There's no gate current because it's the floating gate. So the voltage across between gate and the source, the VGS, and the voltage across drain and the source is the VDS. The current, the conduction current going from the top to the bottom, from drain to source. Output characteristic, ID versus VDS. So in a common source, the ID will be the output current. VDS will be the output voltage. So output current versus output voltage. ID versus VDS. The boundary between trial region and the saturation. On the left-hand side, it's a trial region. VDS is less than VGS minus VT. On the right-hand side is the saturation region, the saturation territory, where VDS is greater than VGS minus VT. VT represents the threshold voltage. This is the comprehensive picture of the device, the output characteristic, ID versus VDS. The blue curve represents the characteristic when transistor in trial region. The family of red curve represent the characteristic when the MOSFET is operated in saturation region, trial and versus saturation. This is the summary. The ID versus VDS is the output characteristic. But there's another characteristic called transfer characteristic. ID versus VGS. In a common source configuration, the ID will be the output current. VGS will be the input voltage. So input voltage versus output current. So it's the transfer. It's a transfer characteristic. ID versus VGS. Saturation region, because you just look at the color. Pay attention to the color. It's a red curve. So saturation is a square law. Because it's the parabola. ID equals half K. Device transconductance parameter. Square law. VGS, the overdrive square. The proportion that VGS surpass the threshold voltage. So square law. So this is the total picture. The blue represent the characteristic in trial, and the red represent the characteristic in the saturation region. So this lecture, I'm going to present the simulation process, some of the key code, and also the result. Let's try to simulate the output characteristic first. Let's do the simulation of the output characteristic ID versus VDS. Now, this is the SPICE, very simple diagram. So 4 terminal. Terminal 1, gate. Terminal 2 is drain. And source and body is connected to the ground. Ground is 0. Well, let's say the ground is 0. SPICE input file. Output characteristic. This is the input file. It says the ID versus VDS characteristic of an N-channel enhancement MOSFET. Let's pay attention to the middle part, all right? The model description. The model description, M12100. So what does that mean? 21, just check the circuit diagram. 2100 means the drain, gate, and source and body. Again, the 2, 1, 0, 0 corresponds to the drain, gate, source, body, respectively. And then EMOS represent enhancement mask, the name of the device. And then model description follow. Dot model, EMOS, right? Dot model, EMOS. The first one shows the connection. And also the channel length, 10 micron, a channel width, 400 micron. And the next one is the model description. The model EMOS is the NMOS, N-channel enhancement. The KP is defined as the product of electron mobility and the gate oxide capacitance. 20 microamp per volt square. So threshold voltage without body effect is 1 volt. And then output characteristic, DC switch command, the red one. Dot DC VDS, 0 to 10 volt. The step size is 10 millivolt. And also the VGS is 1 to 5 volt, and with the step size of 1 volt. So basically scan 2 variables. The number one is scan the VDS. And also from 0 to 10 volt and step size, you tell the computer to do this, the 10 millivolt, do a calculation every 10 millivolt. And also you tell the computer to do the scan the VGS, the 1, 2, 3, 4, 5, 1 to 5 volt. So here's the outcome. All right. So you see the 0 to 10 volt. The horizontal is VDS, vertical is the current. All right. It's the ID versus VDS. This is the outcome. 1, 2, 3, 4, and 5. VGS. Output characteristic. Boundary. So boundary is the boundary between what? Between trial region and the saturation region. Trial and the saturation. So this is the boundary. Right? Parabola. So remember the equation of the parabola is VDS equals what? Overdrive. The VGS minus VT. All right. The simulation of in the next part, we're going to simulate the second characteristic. It's called transfer characteristic. ID versus VGS. ID versus VGS. Spice input file, transfer characteristic. So it's very similar to the previous one, except the VDS is fixed at 6 volt. VDS, just pay attention to the highlight. 2, 0. VDS connected between 2 and the 0. There's the battery, fixed at 6 volt. And then dot DC, the DC switch command for VGS. So you scan the VGS, right? Transfer ID versus VGS. So 0 to 12 volt with a step size of 50 millivolt. Horizontal VGS, right? Vertical is the current, right? Here's the outcome. From 0 to 12 volt, here's the outcome. But if you look carefully, this is a parabola, right? It's a parabola. But it becomes to what? To what? Pay attention. Become a straight line, right? When VGS get higher, it's not a parabola anymore. So it changed. So what happened? This is the result of the simulation, the SPICE simulation. So what happened? Why the parabola turns into a straight line? For ID versus VGS. So now I want you to pause for 5 minutes to think deeper about this. Because it's not just the simulation, right? You have to look deeper. So what's the inside of this? You need to know how to illustrate, explain the simulation result. That's the point. Okay? Simulation itself is not the point, all right? So the reconciliation between the simulation and the hand analysis is always our teaching objective, right? So 5 minutes to think about why the parabola, ID versus VGS, turns into a straight line. So let's pause for 5 minutes. All right, what happened? Why the parabola turns into a straight line? What happened? If you look deeper, then there's a boundary. The interface between the parabola and the straight line is easy for you do the, if you do the simulation, you tell the computer, you just probe, right? So the 7 volt. So after 7 volt, it turns into a straight line. Below 7 volt is a parabola. Then it must relate it to what? The fundamental characteristic of MOSFET. Fundamental characteristic of the MOSFET. Pay attention to this. As I mentioned earlier, VDS is fixed. VDS is fixed at 6 volt. It's connected to a battery with a 6 volt constant. And VGS is a variable. So VDS is fixed. VGS is a variable, right? VGS varies. VDS is constant. All right? So parabola means what? Means the device is in the saturation region. Why? Because think about this. When VDS is 6 volt, when VDS is fixed at 6 volt, and then when VGS is below 7 volt, means what? 6, when VGS below 7, let's say VGS is 6, and then what? Then 6 is higher than 6 minus 1, right? So when VGS, I know it's a little bit, you have to pay full attention, okay? So when VGS is below 7, then VDS is greater than the VGS minus VT, then saturation. Device is in the saturation region. Because VDS, the key is VDS, in this case, in this simulation, is always a constant. And then you can picture, you can just write down, you can get the equation for the parabola based on the square law. The half times, I believe it's 20, right? 400 divided by 10. All right? So 400. So 400 VGS minus 1 square. That's the equation. So here's the what I just said. The half times 20, right? The threshold voltage is 1. And then W over L, 40. 400. What about the right-hand side? The right-hand side, VDS, think about this. What about VGS? What if VGS is 8, 9? Then 6 is less than 8 minus 1. 6 is less than 9 minus 1, right? So VDS in the red zone is less than the overdrive. Trial region. So what's the equation for the trial region? You just pull out the equation for the trial region and plug in all the number, you will see the linear equation between ID and the V watt and the V watt and the VGS. ID versus VGS turns into a straight line. This is why. Here's the takeaway. We use the SPICE to simulate the two characteristics. Number one is the output characteristic. Use the DC switch command. All right, trial and versus saturation. But this is a tricky part. So when you simulate the transfer characteristic, if you keep increasing the VGS, then in a smaller VGS, the device is going to be in the saturation region. You're going to see the square law. But when you keep increasing the VGS, the status quo changed. Okay? The situation is changed. The device is going to leave the saturation into the trial region. And the equation is going to follow the linear equation between the ID versus V and the VGS when VDS in simulation case is fixed. All right, this is the tricky part. I hope we learned something in this lecture. Always remember the teaching objective, learning objective for using the SPICE computer simulation is to do the reconciliation between the simulation result and the hand analysis. You got to know how to interpret, explain the result. Thanks for watching.